Hello, shall we get started? Welcome to the second half of the algorithm session. We're going to hear 3 machine learning talks in this session. Here I'm welcoming the first speaker, Chang. He's actually a PhD student from Caltech in the physics department working on CMS experiments. And he works on optimize the networks for sub-microsecond inference FPGAs targeting the CMS level 1 trigger, and is a maintainer of the HRS4ML library. We're going to hear extension of that today. It's the DA for ML, distributed arithmetic for machine learning on FPGAs. So Chang, welcome. Please get started.
Okay, so this is basically an introduction to the DA4ML library and its algorithm on implementing the fast neural networks on FPGAs. And this is on the implementation side. So I will skip the network quantization and training part and directly into how do we make the network itself directly onto the chip. So before I start, how many of you have heard of distributed arithmetic? Okay, not many. So I will give some introduction. And DA4ML is basically a library that optimizes the CMVM operation, that is a constant matrix vector multiplication. And it can do either C++ or Verilog code generation. And for some neural networks, it can also do the full formula generation. And this is basically a high-level introduction for the library. And I will talk about what is CMVM and what is distributed arithmetic for it. So there are basically 4 kinds of operations that are frequently mentioned in the context of distributed arithmetic. There is a single constant multiplication. So basically, you have a constant multiplies a number. In this case, you can basically do what you want to do on FPGA is you do a series of shift operations, and it just accumulates the shifted sum. And you have the MCM, which is probably the most mentioned topic in the literature 10 years ago, which is frequently used in the transpose FIR filter. So basically, you have one variable and a series of constant vectors, and you want to multiply this variable to all of those constants. And the results can be used in the downstream, and in particular in the FIR. And there's also the non-transpose FIR, which is basically the CMVM. It's basically a vector dot product between a constant and a vector. And we have the most general form, which is CMVM. That is a constant matrix and times the variable vector, which is a general linear DSP operation. And we are focusing on optimizing this kind of operation on chip, which is the predominant part of the fast neural networks if you implement it on the FPGA. So what is distributed arithmetic? It's basically if you have a MAC operation, whether it's any form of from the previous page, you can implement it as an adder tree, basically, or adder graph. And this is a dump implementation. You just do the shift sum, or you see here, because every number is already a power of 2. So you don't have to decompose each number into some sign digit representation. It's directly a shift. But in the general case, you have to decompose each number also into some sign digit representation. And for each of the expression, in this case, y, is basically a CMVM. And you can also see that this can be implemented as an adder tree on the right. So here you have basically many addition and subtractions, and you need here 12 adders if you do it in the dump way. However, so basically the CMVM operation, if you implement it in this way, it is not very efficient, but it's currently what the compiler is actually doing on the background. And what we do here to optimize this operation is in a hybrid algorithm. I'll explain the details in the next slides. So basically, we have the first stage is pre-optimization with a constrained minimal spanning tree to to transform the expressions into a simpler form. And the second one is a greedy two-term sub-expression elimination. And this algorithm poses around 2% overhead compared to the SOTA, which is basically the hybrid CMVM from more than 10 years ago, but I cannot find anything newer than that that's performing better. And it's much more faster, and both in constant and asymptotically. So first, we have to decompose constant matrix into some powers of 2 representation. And the representation we adopt here is the canonical 7 digit. So for example, if you have a number 7, if you represent it in binary, it will be 0, 1, 1, 1. That's trivial. But in 7-digit representation, you can have many different representations, all representing 7 here. So you can have, for example, there are 4 representations here. You can have either the binary 1, 1, 1, 1 here, or you can have 1, 8 minus 2 plus 1 is also 7. And you can have also 8 minus 2, sorry, 8 minus 4 plus 2 plus 1 is also 7. And you have the last one, 8 minus 1 is also 7. So you can see that the number of digits you need for representing each number is different. And the representation requiring the minimum number of non-zero digits is called the minimum 7-digit representation, MSD. And the canonical 7-digit representation is one of them, which is easy to implement. So we adopted. So basically, this is a minimum 7-digit representation that requires any of the 2 consecutive 7 digits in the 7-digit representation cannot be both non-zero. And this will basically have around 66% sparsity if the digit is significantly long, but that's another story. So first, we represent the constant matrix in this form, and then for each representation, we put the representation as a node in a graph, and we also put a node that is 0. That is our starting point. So we start with nothing, and we want to reconstruct all the expressions. The trivial one will be connect 0 to all of your expressions in the graph. They will basically give you identity transformation, which is actually in many cases the solution, but in some cases you can have a better solution. So for example, in an extreme example, you have a constant matrix, or all of the rows of your matrices are the same. So you basically want to broadcast the same results to all the outputs. And in that case, the distance between the different nodes will be 0. And the distance is defined by you have the sum and the subtract between the representations, and you compute the number of digits that is non-zero in the CSD representation or MSD representation. And it's a smaller one between these two. And basically, you can construct an alternate program that is equivalent to the original CMVM problem, but can be easier or actually harder. But this part needs some scanning, basically. And the reason we didn't do iterative algorithm like the HCMVM is that it would be too computational costly, and doing a minimal spanning tree is basically instant with a complexity of n squared. And the second part is the most important, or the core part of this algorithm is a greedy common sub-expression elimination. So starting from the set of expressions, again, of y being some constant dot product some variable, and for each term, basically a constant times a variable, and the constant here is any power of 2 plus minus 1, and find the all occurrence of this expression up to any powers of 2 and assign. So this is to basically gather how many times this part of the expression appears in the whole CMVM problem, and find the most common one as having the highest frequency, and to implement it. By implementing, I mean just evaluate the input a xi plus minus xj times 2 to the power of n, and 2 times 2 to the power of n is implemented by hard wiring, so it's not a real operation on FPGA comparing to identity. And just repeat the third step until there's no more. And this is an example of how this operates in the H264 matrix. So here you can see that there are basically 3 common sub-expressions. The first one being x0 plus x4, and there's x1, and there's x1 and x2 plus or minus. Both of them have a frequency of 2. So starting from the one with the highest frequency, we just implement it by adding an x4 equals to x0 plus x3. That is one adder, and you remove the 3 required adder by this pre-computed results, and you just iterate. The second time, we randomly choose between one of the remaining sub-expressions, and just repeat until this finished. We can have, instead of 12 adders to implement the H264 matrix, we can have a matrix of only 8 adders instead of 12. And this is directly translates to less FPGA resource utilization. So the algorithm I mentioned, it compares to the HCMVM, which is the current SOTA, though a bit from 10 years ago. Is almost identical performance when the delay constraint is not imposed, or the delay constraint is not imposed to the maximum extent. Basically, you have to require the adder depths to be exactly the same. So in this case, it's the same. You need at least 2 layers of adders. But in some cases, this will be different, or actually in most cases, it will be different. And these are the exact numbers. So we checked against random matrices generated by n size. And all of them are, each of these elements is a uniform distribution of the 129 to 255, which is 8 bits. And it's a very different definition, but it's used in the original paper. So we basically follow this convention. And we observe around 2% overhead in terms of adder count. And the overhead is higher when the delay constraint is 0. So the adder tree is at its minimum depth. Though there are some known bugs actually found to be probably causing this, but another story. So this is basically a visualization of the table as shown in the previous slides. So here for the no delay constraint case and the minimum delay constraint plus 2 case, we are basically recovering the performance of the HCMVM. And for the delay constraint with minimum adder depth, we are around 8% less efficient, though there's a bug. So this will probably be recovered later. However, if without any context, we are just reinventing the wheel with a less performant algorithm. Why? Because the HCMVM is just too slow. It's basically scaling to the power of 6 to 7. And because the HCMVM implements both a look ahead and iterative in the MST stage, where we just did a quick scan over the MST. And the result is that for a 16 by 16 matrix with 8 bits, while our algorithm takes around 30 microseconds to complete, this HCMVM will take around 20 minutes. And this basically forbids it to be really applicable to a matrix with higher dimension, say 64 by 64, though it's probably too big with full 8-bit matrices. And certain neural networks may have bigger matrices, and the number of times this algorithm needs to be run can be pretty high. Say you have a CNN, and if you want to recompute for each of its kernel, it can be very slow. And in contrast, the algorithm we proposed finishes our 128 by 128 matrices of 8 bits within around 2 minutes, which is reasonable. So, and this matrices is basically the maximum size you can reasonably fit into XCVU 13P within one superlogic region. So we concluded that this algorithm scales to the extent that is reasonably required by this application. So this is just the algorithm, and we have implemented the DF4ML library that talks to the HS4ML. So in this case, we trained the neural network with AGQ, which is a heterogeneous quantization library down to the per parameter or per weight per activation level. And so this level of granularity is useless outside of FPGA or ASIC in the fully unrolled region. But on the contrast, it will be very useful for FPGA. And because we have a fully heterogeneous weights and activations, there can be some overhead if you implement it on DSP or other fixed weight logic. And distributed arithmetic is likely a perfect solution for this because of sparsity is no longer relevant if you transform it into adder tree. And the workflow is like this. You basically, the example here uses AGQ, but it can be any other front end. So you have your network translate to HS4ML, and HS4ML will basically send the individual CMVM problem to DF4ML and does optimization and the code generation in the HRS backend. In this case, only the AP fix type. So Vivado type is well tested. And you can generate to the Vitest and Vivado. And everything is pretty exact. And here are the results. This is a very small neural network with like 97% sparsity. So you cannot really do a lot with the distributed arithmetic. Nevertheless, you can see that the number of loop usages is slightly lower here, and the number of DSPs used is basically eliminated. So you get some free resource reduction without accuracy compromising. And this is another neural network that is SVHN classifier, which is bigger, and you can see that the load usage here is much more significant, around 40%. And you also have a lower latency, so the latency here is not very relevant because it's mostly the latency arises from the multiplexing the same filters. So each filter gets marginally faster, doesn't really change the overall latency. And you have another regression neural network that you have some resource reduction and a DSP reduction also. And in this case, if you don't use the DA4ML, the HS compiler actually fails to achieve the required initiation interval. So the results without the DA4ML should be taken with a grain of salt. So this is one working mode for the DA4ML that is working with HRFML, but it can also directly do a symbolic tracing of neural network that gives a full adder graph and directly generates a Verilog code. And this can be very useful when the network is more heterogeneous. So for example, in the next slide, I will show an MLP mixer. And in that case, because the input bit widths are also heterogeneous, so you want to optimize the CMVM with respect to each input, and optimize the adder graph based on that. If you do that in HRS4ML, it will be super slow. Basically, the HRS code generated will be too long. And as a reference, so this is how it actually works. And you have also the variator integration and other things. And the inference is pretty fast. But this is a story. So basically, in the Verilog coding, we have around 2% overhead comparing to HRS. However, the speed is much more faster. For example, the MLP mixer shown here will take around 17 hours to sync with HRS. But if you generate a Verilog, it will be 30 minutes and in a higher granularity. If you use the same granularity in HRFML with HRS, it will basically never finish. Around 17 hours times 30 or 60. And we are achieving better results here comparing to the HRS because using higher granularity. And we also have a very exact resource surrogate, basically counting the adder count, and it's very linear. The deviation from the TGC or the muon tracker is basically from a non-DA4ML implemented layer that is using 1-bit masking operation that is not modeled, so it's not here. But otherwise, the resource surrogate is around a few percent accuracy. And just showing some floor plan. So in Xilinx, we achieved around 20 megahertz, and if you insert a bunch of registers, you can clock it up to 800 megahertz. And that's it. Thank you.
Thanks, Chang. Questions or comments? Go ahead.
When in your intermediate terms, you are doing addition, so you have intermediate results which are larger than the inputs.
Sorry, I cannot hear.
Sorry. So thank you for the talk first.
Sorry.
In the intermediate terms, you have more bits than in the inputs, right?
Yes.
So since you are exploring various intermediate terms, this should be taken into account in the cost.
Yes. Actually, in the resource surrogate part, we account that. And also in the algorithm part, actually, we weighted everything by its number of operations needed. But that will be too much technical detail, so I didn't include it in the slide.
Any other questions? Look, go ahead. There was another person.
Great work. Consider I have somewhere a weight 6 and somewhere else a weight 12 or 24, which is just a power of 2 multiplied of the 6. Can I recycle that somehow efficiently in your approach?
To cycle what?
So if I have to multiply at one point, let's say with 6, And at another point in my matrix, I have to multiply with 12, which is 2 times 6.
Yes.
Can I recycle this efficiently?
So because in the because here when we count the common subset expression, we counted anything up to power of plus minus 2 to the n. So technically that should be counted, but depending on the exact pattern, maybe when eliminating other expressions, that part is damaged or partially eliminated, so that the exact pattern is not always recognized. But if you have a 12 and a 6 just sitting there, it will be.
Then I have a second one. Is it really desirable to have super large matrices? Isn't it better to have multiple smaller ones that fit the size of a convolution window so that I can maximize the amount of compute I can do per unit I/O? And if I play that game, can I recycle across multiple convolutions eventually my multiplications?
So if you want to do that, you have to use the HLS way at the moment, because the HDL generation will be a fully static pipeline. But when working with HS4ML, if you have the same CMVM matrix, it will be recycled many times. For example, in the SVHN network shown here, given the initiation interval of around 1,000 cycles, it's actually the same matrix is cycling there with the same logic.
Okay, thanks.
You have a question?
Yes, thank you. You mentioned that the Verilog implementation is bigger than the HLS implementation. Do you know why? What's the difference?
Probably because the Verilog implementation is not super optimized at the moment. And also so basically I wrote the shifted adder module, and currently it's by some explicit padding when you do the shifting, and that part can break some compiler heuristic, I guess. But the exact reason is not known at this moment, and that needs more investigation.
Any question? Go ahead. You?
Yes, I have a question. How did you implement Verilog generation? Just by string concatenation, or
So the Verilog generation. Within the framework, we actually translate it into some assembly code latency. Is actually you have some opcode. You tell each step you have a buffer to multiply and or subtract. Sorry, to add or subtract power of 2 of the A plus minus B, and you implement a module to do this, and you just do the code generation in a single static assignment form.
So you have a compiler-like design?
It's a compiler-like, but it's not a full compiler. It's basically it's like a DSL in Python.
Have you considered something like Circuit? Are you familiar with Circuit?
Sorry, Circuit what?
Circuit is an MLIR-based hardware.
Could be, but currently we directly goes to Verilog, but to go to MLIR or other things are also possible. And then we can also benefit from some of the HRS heuristic.
Okay, thanks.
All right, any other questions? Okay, if not, let's thank the speaker again, Chang. Thank you so much. Let's move on to the next slide.